So let's have a look at water of crystallisation. So some ionic compounds are going to look much more crystalline than others. So some of them are going to look powdery and dry, and others are going to look like crystals. So salt is a good example of something that looks very crystalline. Copper sulfate crystals, you might be familiar with, always look very crystalline. So nice and shiny and have a crystal shape. When ionic compounds have water molecules surrounding the ions, then that is when you get this kind of crystal shape, and they're called hydrated salts. So we have some terms. So a hydrated salt is a salt which contains water, and it's specific waters. Let's add that, it's water of crystallisation. So waters that have been trapped in the crystal structure. What do we mean by crystal structure? Well, remember that in bonding we look at ionic crystals as going positive ion, negative ion, positive ion, negative ion, but there's some water trapped between those ions. And the number of waters that are trapped, those waters of crystallisation, are shown by the formula. So copper sulfate, we might be familiar with the formula as CuSO4. If there's a dot, it's not like maths, it's not a timesing, it means that there are 5 waters of crystallisation in copper sulfate crystals that are hydrated. And one of the things that chemists need to find out is how many water molecules are trapped per crystal per formula unit of the crystal structure. And to do that we've got 2 methods. We can either do that by evaporation or we can do it by titration. So we're going to look at each of those methods. When we heat them up and drive off the water, then our thing is going to become anhydrous, and we're going to separate. So they're both solids, and we're going to remove the water as a gas, as steam. Now when we look at copper sulfate crystals, these are our hydrated, with the water of crystallisation trapped, and they appear blue in colour, and these are our anhydrous crystals without the water, and they appear white in colour for copper sulfate. So these waters of crystallisation are an essential part of the structure. So how would you do it? So method number 1, can you do it by evaporation? So to do that you're going to need to know the masses of both the hydrated, the crystals at the start, and the anhydrous. This will sometimes be referred to as the residue weighs, it might say in the question. The mass of water is going to be the difference between the two, because the water was driven off, and we can use that to work out moles, and from moles we can work out ratio in a similar way to doing an empirical formula. So if we have a look, we've got CuSO4, oh no we haven't, let's get the right formula, FeSO4, and we don't know how much, so we've got an X, and we're going to heat it up, and we're going to get FeSO4, and the X moles of water are now going to come off. Now what we've been told in our question is that 6.95 grams of this were heated and 3.80 grams of this remain. So to work out the mass of water, according to the conservation of mass, 6.95 minus 3.80 equals 3.15 grams, and we can put that here. There must be 3.15 grams of water. Now what we need to do is work out the molar ratio for every one of these, how many of these are there, and to do that we need to convert mass to mole. Let's put our masses in, 3.8 and 3.15. We're not now using the 6.95, we use that to get the water. We add up the MRs, so we know that water's MR is 18. And we add up the MR of FeSO4 using our periodic table. Convert the masses to moles, so divide mass by MR, and you should get 0.025 here, and if you divide 3.15 by 18 you get 0.175. So convert mass to mole. Now divide by the smallest. We get 1, and divide 0.175 by 0.025, and you should get 7. So the formula is FeSO4.7H2Os. There are 7 waters for every iron sulfate. The other way you could be asked to work this out is by using a titration. So let's have a look at our information for titration. 27.3 grams of the hydrated crystals were dissolved and made up to 1,000, and 25 of this needed 48.8 of 0.1 mole of nitric acid for neutralisation. Let's just have a look at our experiment visually. We've got our volumetric flask, although we could draw that a little bit better than that. And in there we've got 27.93 grams, but we don't know the MR because we don't know what the X is, so we're going to be calculating MR, very similar to the pages about further titration calculations. There was 1,000 centimetres cubed here, and then we're going to put 25 of it into a conical and titrate it with 48.8 centimetres cubed of 0.1 moles per decimetre cubed nitric acid. So where do we start with our calculation? Remember that we can start here because we know moles, and we're going to work our way back in this direction. So number of moles of nitric acid, 48.8. Remember to convert to decimetres cubed. Now we need to move from our burette to our conical flask, and we're changing chemicals, so we need to use the ratio. Let's have a look at the ratio. We've already got the moles of nitric acid, and we need the moles of sodium carbonate. There's 2 nitric acids there for every 1 sodium carbonate, so that's 2 to 1. So the moles of sodium carbonate in my conical, which was 25, so in 25 centimetres cubed equals, well, we had to go from 2 to 1, so we divided by 2. And now we need to go from our conical to our volumetric, so we need to scale up. And we're going from 25 this time to 1,000. So how many 25s are in 1,000? We're going to times by 40. So the number of moles of Na2CO3 in 1,000, 2.44 times 10 to the minus 3 times 40, 40 times more chemicals, 0.0976. So we now know how many moles are in our volumetric flask. We also know the mass. So if mass is Mr. Moles, then MR is mass over moles. We know we had 27.93 grams, and that it was 0.90976 moles. So we can work out the MR, and the MR would be 286.2. Now we know that this is the solid, and this is the Na2CO3.XH2O, and it comes to 286.2. So we just need to use our periodic tables to find the things we know, which is the sodium, the carbon, the 3 oxygens, and then we've got X lots of water, and water weighs 80, and we know that that comes to 286.2. So do some algebra, rearrange. I'm going to get 18x is 180.2. So x is pretty much bang on 10. Now it's a number of waters of crystallisation, so we want a whole number in that spot.